Welcome everyone to today's video. For today's video, we're going to talk about decomposition chemical reactions. We're at the start, we're going to explain just really quickly what it is, and then we're going to dive in how to predict products for these types of chemical reactions when you encounter them. In a previous video, we talked about synthesis chemical reactions. These are just the opposite of decomposition. I'll explain kind of how that is when we start talking about what it is, but if you want to watch that video on synthesis chemical reactions, should be up here at some point in the video saying synthesis chemical reactions. With that said, let's go ahead and get started. Okay, to briefly summarize what a decomposition chemical reaction is it's just a chemical reaction where one substance decomposes into two or more products. This is just the reverse of the synthesis chemical reactions, where instead of going A plus B, whatever those elements were, combining them in a chemical reaction to form one product, we are going from that one product into two different substances. One common example that we use on an everyday basis is hydrogen peroxide, where we have H2O2 sitting in that brown bottle, and then when you use that for its cleaning purposes, you end up with H2O plus O2. This is just one example. We are going to look at several other types of examples for the sake of this video. Let's go ahead, dive right in. Okay. Predicting products. For this type of chemical reaction, this might be the simplest of all the predicting products for the most part. All you're doing is looking at the makeup of that particular compound or molecule that you're starting with in the reactant side, and then you're just writing the individual elements over here. So hydrogen was one, oxygen was the other, and when you write them out over here, the only thing you need to look at is that list of diatomic elements that was previously mentioned. The acronym is Hofbrinkel. That is hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. These are usually or almost always diatomic. That is, they always have a 2 following their atomic symbol. So water, when it undergoes something similar to like electrolysis, will split into hydrogen and oxygen gas. These gases always have that 2 afterwards, because hydrogen is part of that diatomic list, and same with oxygen. So that's all you have to do for that. That's literally all it is. Separate it out, see if it is a diatomic element, and then it's all good. You don't have to do any sort of valence charges to see how they will interact with each other to rewrite it on the other side. Let's go ahead and take a look at, we'll do 2 more examples. Okay, another example would be like table salt, sodium chloride. When you run electricity through it, this also separates the 2 in a form of electrolysis. So first thing we do is we just write the 2 elements that exist in there over on the other side. Take a look at sodium. Is it part of our Hofbrinkel acronym here? Nope. So we're all good. We'll take a look at chlorine. Is it part of this? Yes, over here at the other one. So we just put a 2 after that. And then that's it. That's done. Keep in mind that we are not balancing these chemical equations here. We will do that in another video later on in the future when we talk about balancing chemical equations. Let's go ahead and do one more example. Okay, last example, say we have rust, I guess is what this is, Fe2O3. It's typically what you see growing on bike chains after you go ride them in the rain. Same thing, we just follow the same steps there. This is made up of iron and oxygen, so we just write the 2 elements over here. Make that a better looking E, there we go. And then is Fe a part of this? It is not, so we leave it as is. Oxygen is part of that, so we put a 2 there. That's all for the examples. I do want to go over a couple notable examples of some very, very common decomposition reactions that you see on a regular basis, whether it be in the home or through common chemical reactions that you might see in a chemistry lab. Let's go ahead and take a look at those really quick. Okay, I just wanted to talk about a couple examples that it's not usually as straightforward as it is with the other examples where you just separate the two. These are two common molecules that exist out in nature that they rarely ever stay in this form. They almost always convert into or decompose into these two products. And there is, I'm sure, a way that we could do it, but to keep things very simple, which is the purpose of these video series, the only real way to recognize and know that this is the decomposition reaction for these two molecules is just to kind of memorize them. And this is carbonic acid. Carbonic acid is really common when you're using things like baking soda to neutralize an acidic solution, say taking baking soda and putting it in vinegar. One of the products that occurs from that is carbonic acid. It's also what gets formed in water when carbon dioxide is introduced into water. If you just took carbon dioxide and blew it into water, the water would become slightly acidic. This is basically kind of like the fizz, you could say, in soda pop, where the carbonation gets added to water to make it a little bit more fizzy. It's that carbonic acid that also forms a little bit there to allow the CO2 to dissolve. Anyway, when carbonic acid is formed, it's pretty unstable. It never likes to stay there for very long. When it decomposes, it almost always converts into H2O and CO2. And basically just these two hydrogens in here will combine with one oxygen. Carbon will take the other two, and then they'll separate out into more stable molecules. Another example, and this is why hydrogen peroxide usually comes in those brown bottles so that sunlight can't hit it, is hydrogen peroxide decomposing into water and oxygen gas. There's a couple cool examples that you can do with matches and using like manganese dioxide or potato peels even to kind of just quickly decompose hydrogen peroxide and release this oxygen gas. And you take a matchstick that's only slightly lit and it'll make the fire kind of go because it's producing the oxygen gas. It's a neat thing. We'll do a video of it in another day. But hydrogen peroxide, I mean, if we had to split these two out, normally we would just go H2 and O2, but that's not what happens. What happens is water will separate out, and then whatever is left, those oxygens that end up leaving this hydrogen peroxide will end up making an oxygen gas molecule and taking off, leaving into the air. This is what those bubbles are when you see them decomposing. So that's all for today's video. I just wanted to talk about these examples really quick just because they're pretty common, and you wouldn't get that from how I just showed you to kind of predict products of chemical reactions there. You just got to kind of know that this is what happens. If there's a way how to do it, you let me know in the comments, or I'll make, if I learn how to do it, I'll make a video on it in the future. Anyway, hope this was helpful. If it was, leave a like, subscribe to the channel. It really helps. And thank you all for watching. Take care.